Okay, in this lesson, this is for Algebra 2, Unit 4, Lesson 3, we are reviewing on how to simplify square roots, and this will build into how we solve quadratics by taking square roots, which is a really fun method to get to use. Now, simplifying square roots. Okay, square roots, they go hand in hand with a radical. Okay, a radical, right here it says, is any expression with a square root, a cube root, etc. So this is our radical symbol, just like that. If there is no little number on the outside of this radical, no index, then you're just taking a square root. Okay, a cube root would be when we add that index, we would have a little 3 on the outside. You can also do fourth roots. This would be fifth roots, etc. Now, perfect squares and square roots are those inverses. They're opposites of each other, so they go hand in hand. So to know how to take square roots, we need to know what our perfect squares are. So to find a list of perfect squares, you just think of like the numbers when you're counting. What are they equal to when you square them? So if I said, what is 1 squared? That would be 1 times 1, which equals 1. So that's on my perfect square list. 2 squared is my next, 2 is my next number, so we would do 2 squared. That's 2 times 2, which is equal to 4. So that's a perfect square on the list. Okay, we're making the first list of 20 perfect squares. 3 squared is 3 times 3 is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196, very similar. 15 squared is 225. 16 squared is 256. 17 squared is 289. Then we have 18 squared, which is 324. 19 squared is 361. And 20 squared, 20 times 20 is 400. So that's just a list of our first perfect squares. I know my up through 15 really well by now because I just use them so much, but the better you come to recognize what a perfect square is, the better you're going to be able to do it doing square roots method. But your calculator also loves to do square roots, especially if you get a Casio like I recommended. You're going to just like think this section is a breeze. If you're using a TI calculator, you're going to have to do this method by hand, and it's going to be more of a struggle, but totally doable. Okay, so simplifying radicals. When we simplify, we have 2 different cases. If we're simplifying radicals and we are dealing with perfect squares, numbers from this list, then we just take the square root of that number, we get a whole number in return, and we are done. It's pretty awesome. Or we have case 2, where we have non-perfect square roots. This is when we have to break the radical down using the largest perfect square. So when there's a non-perfect square that we're trying to take the square root of, we don't want to write down a decimal answer. That's gross in algebra. We don't do it. But just because that the whole number we're taking the square root of doesn't work out evenly to a whole number, doesn't mean that we can't take a square root of part of that number. So we break it down into factors. We're looking for a factor, the largest factor of the number that is a perfect square. We could take the square root of that and leave the rest of it inside the parentheses, and we'll show how to do that. For both cases, there's a coefficient outside if there is a coefficient outside the radical, multiply this with any number you take out. Okay, all of this will be practiced. But if you don't like case 2, get yourself a Casio calculator like I asked you to. It does it for you. I call it magic calculator because it's like magic. You don't have to do all that work yourself. Okay, on our first 6 examples, we are dealing with perfect squares. So if I was asking you to find the square root of 49, well, 49 again is made up of 7 times 7. To take the square root of something, you need the same number twice. Okay, so because I have 2 7s, 1 7 can come out. Or you just type it into your calculator, square root of 49, out pops 7. It's pretty great. The square root of 225 for number 2, what number times its own self equals 225? Remember, that's on our list. That would have been the square root of, that was 15 times 15. So the square root of 225 equals positive 15. Now, all calculators do perfect squares. Now, in number 3, we're saying 2 times the square root of 144. Okay, so what number times its own self equals 144? That was 12 times 12. So what's coming out of here is 112. Okay, 112 gets to come out because that's the square root of 144. But we already have this 2 on the outside right here. So we're going to say 2 times whatever comes out of the radical, which was 12. Then we have to multiply those two to get 24. Again, above this is being read as 2 times the square root of 144. So 2 times whatever comes out. Okay, on numbers 4, 5, and 6, we're still dealing with perfect squares. We have perfect square fractions. When you're taking the square root of the fraction, we're just taking the square root of the numerator and taking the square root of the denominator. For example, on number 4, the square root of 4/9, well, the square root of 4 is 2, so that's my new numerator. The square root of 9 is 3. It was 3 times 3. So the square root of 4/9 is just 2/3. On number 5, we're asking to take the square root of 1 over 81 over all of it. And again, both of 1 and 81 are perfect squares. So the square root of 1 is 1, because 1 times 1 makes 1. The square root of 81, okay, that was made up of 9 times 9. So the square root of that is 9. Our answer is 1/9. Whoops, circle, pin. And number 6, we have 36, the square root of 36 over 121. Okay, they're both perfect squares. The square root of 36 is 6. That's what comes out. The square root of 121 is 11. So my answer is 6/11. Okay, these examples for 7 through 12, we're going to be asked to take the square root of numbers that are not perfect squares. For example, if I typed in the square root of 112 into my calculator, and I'm not using a Casio, this would tell me 10.583000524, and it keeps going. That's an irrational number. That's crazy. We don't like it in algebra. So we simplify the radical. We take the square root of a part of 112, okay? So we're going to break it into factors. Remember, factors are numbers that multiply to make another term. Because there's a factor of 112, a piece of this I can take the square root of. So I have to think back to that list of perfect squares I had. 1, 4, 9, 16, 25, 36, and so on. Okay, one of those numbers is a factor that makes up 112. Now we have a nice rule of thumb here. Okay, we don't like this answer. Where our perfect square factor that we're looking for cannot be more than half of what we're taking the square root of. So I'm going to start by dividing 112 by 2 if I'm doing this longhand. And that gives me 56. So from my list of perfect squares that you have on your notes now, I'm looking for a perfect square that goes into 112 that's lower than 56. All right. So then it's a lot of trial and error if you're doing this by hand. But I would think lower than 56. Does 49 divide evenly into 112? No, it doesn't. Does 36 divide evenly into 112? It does not. And 25 does not. But once I get to 16, that divides evenly into 112. Because 112 divided by 16 is 7. So we are going to rewrite this problem that we have here. I'm going to kind of move this over. This can be rewritten, okay, as 16 times 7. And notice I left that all underneath the radical here. It's all the same, the square root of it, but 16 times 7 is the same thing as 112. So I'm just showing it in a different way. But I'm doing it like this because I can take the square root of 16. So the square root of 16 is 4, because 4 times 4 makes 16. So 4 gets to come out of the radical. 7, he's like the leftover. He's a reject. He's not a perfect square, so he is staying underneath the house. So as a simplified radical, this would be 4 times the square root of 7, and it's done. Now, the thing is, if you have a Casio, your Casio, if you type in the square root of 112, it does give you the simplified radical. It does say 4 square root 7. So it's kind of like magic, I say. So get yourself a Casio if you don't like this method. On number 8, we're taking the square root of 245. Again, if we type that in, we would get a big fat decimal. So we don't like it. So I'm going to go through the process of finding what is the largest perfect square value that goes into 245. So I'm going to start by making myself a little list here of perfect squares. Okay, from looking at my notes, I know that it's 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and so on. Okay, that should be good enough. So again, the rule of thumb is to take what is underneath the radical and divide it by 2. The number from this list right here that we're looking for cannot be more than half the number underneath the radical. So 245 divided by 2 is what I'm checking for first, gives me 122.5. And again, I'm using this just as a starting place for the list. 122.5 fits in between 121 and 144. So I'm going to start by checking 121. Does that number divide into 245? When I divide 245 by 121, I get 2.02 something. If you divide these numbers and you get a decimal, then that means that perfect square was not a factor. It has to divide evenly, give you a whole number answer. So I'm crossing it off my list. And then I keep working my way down. And again, why do I start here in the middle and working my way down to the smaller values as opposed to starting with 1 and working my way down? Okay, we always work from bottom, from that line we find, down to 1 because we are looking for the largest perfect square. That's a factor. If we started at 1 and worked our way up, we might not get the largest number. That's a factor. We might just get a smaller number. So I divide 245 by 100, it gives me a decimal. Okay, and you can just be really quick about this if you're doing it by hand. Any decimal, we just cross off the list, like 245 by 81, decimal. 245 divided by 64, decimal. But 245 divided by 49 gives me 5 as an answer. That means that 49 and 5 are both factors. So we're going to rewrite number 8. Okay, this is the same thing as 49 times 5. And why do we like this better? Because while we couldn't take the square root of 245 without getting a decimal, we can do the square root of 49, just the piece of this. The square root of 49 is 7, so 7 gets to pop out. And 5, can't take the square root of 5. It's not a perfect square, so it stays underneath the radical. Our simplified answer is 7 times the square root of 5, excuse me. Okay, for number 9, we have 5 times the square root of 72. Again, 72 is not a perfect square. So I need to go through this process if I'm not using a Casio. My perfect squares are, again, 1, 4, 9, 16, 25, 36, 49, 64, and so on. So I'm going to start by taking that number underneath, 72, and I'm going to divide it by 2. And that equals 36. Again, this gives me a starting place on my list of perfect squares to use. Now, 36 is on my list of perfect squares. So I don't have to do any extra work here. I've already found the largest perfect square that makes up a factor of 72. So we are going to now rewrite this as 5 square root, and this is going to be rewritten as 36 times 2. Now, whatever comes out of the radical has to be multiplied by 5. So we're going to say this is 5 times what's coming out of the radical, the square root of 36 is 6. So 6 and 5 will be multiplied. 2, we can't take its square root, so it stays inside. So 5 times 6 on the outside is 30 times the square root of 2. Okay, for number 10, we have 9 times the square root of 45. So again, 45 is not a perfect square. So thinking of my perfect squares, I'm going to make a little list right here. Okay. So I'm a starting point again. I'm just going to keep going over this even though it's kind of redundant. I'm going to take half of the number inside. So 45 divided by 2. What does that give us? 45 divided by 2 is 22.5. Okay, so again, gives me a starting point on that list. It's in between 16 and 25. So I'm going to start 45 divided by 16, and I get a decimal. So it's not 16 that I want to use. 45 divided by 9 results in 5. So 9 is the perfect square that I want to use here. We'll write this as 9 on the outside. Then we have the square root of 9 times 5. That's the same thing as 45, but written to show the part we can take the square root of. We can take the square root of 9. What comes out is the square root of 9 is 3. Again, that has to multiply by what's ever on the outside. We're going to do 9 times 3, and then the square root of 5 stays underneath. 9 times 3 is 27. Again, 5, that part that's not the perfect square, stays underneath the radical. Okay, so we have 11. We have the square root of 250. Nothing on the outside, so we won't have any extra multiplying here. So right now I'm just thinking, oh, hey, ends in the 0. I'm thinking that's the same thing as 25 times 10, and 25 is a perfect square. So already, just by looking at it, if you recognize the part that is a perfect square, you can kind of jump to that conclusion already, or you could just do the list and be very procedural that way. Both are right ways to do it. Neither is wrong. So I'm going to rewrite this as 25 times 10. Again, it equals 250, so I can rewrite it that way. I can take the square root of 25. Out comes 5. 10, its factors are 5 and 2. Neither are perfect squares. Okay, that part, even though it's even, it's going to stay underneath. So it's 5 square root 10 as my answer. And again, Casios go from here to here if you have a Casio. For all of these, they're pretty wonderful. Okay, like my plug. I'm not getting any kickbacks from Casio, by the way. It just makes my teaching life so much easier if people have a Casio calculator. So we have 3 square root 578 for number 12. So when I start my process here, again, I'm going to do 578 and I'm going to divide it by 2 because it can't be more than half of what's underneath the radical. So 578 divided by 2 is 289. Well, 289 is 17 squared. It was on our perfect squares list. So if you're not sure, maybe keep that list nice and handy. So we've already found the two numbers we want to use, 2 and 289. So we will rewrite number 12 as 3 and then the square root of 289 times 2. We can take, again, didn't mean to do that, we can take the square root of 289. It comes out as 17 because it's 17 times 17. So we are multiplying whatever's on the outside by that number. We're doing 3 times 17, and then the square root of 2 stays underneath. 3 times 17 is 51, so the answer is 51 square root 2. Again, the whole goal here is to rewrite it with the remainder part of the radical still underneath that house. We don't want any decimal answers here. So how does all that square root business apply to solving quadratics, what we've been doing? When we have a quadratic equation in the form of ax squared plus c equals 0, we can solve this by using our square root property. So in other words, okay, there's no bx, so there's no x term here. We're missing that middle value that everything else has. We have the x squared and then we have the constant. When that happens, we can solve for x squared by getting x squared isolated. So that's what step 1 says. Isolate x squared. That means get it by itself on one side of the equal sign. Then to get an x squared to turn into an x, we take the square root. And what we do to one side, we have to do to the other. So we're doing it to both sides. Why can't we do this for the other methods? Because you can't take the square root of a term that has just a regular x. Okay, you can take the square root of x squared. You can take the square root of a number. You can't take the square root of something that's just x. So this is why this method, it's pretty quick and fast if you recognize it. And then if it's not a perfect square, we simplify the radical like we've been doing. Now when you take the square root of something, when you're solving for x, we have to put a plus or minus sign to indicate both answers. Why do we have to do that? Okay, if I'm saying x squared is equal to 49, what we're asking is what value when squared equals 49? Why is there two answers? We know that the answer is positive 7 because if I plug 7 in for x, I do 7 squared. 7 times 7 is positive 49. But we get a second answer because when you plug numbers in for x, you have to use parentheses. So if I plug in negative 7 and square it, this again means negative 7 times its own self, negative 7. And a negative times a negative equals a positive. So positive 49. So 7 and negative 7 are two completely different x values. Okay, they're on opposite sides of the x-axis, right? Okay, we would have positive 7 and negative 7 that our parabola would be passing through. But again, when plugged in for x, they both result in the same answer, positive 49. So you always, always, always put this plus or minus sign on both sides. Now going back up here, that's why I hesitated earlier. If x squared equals n, then we are saying that x is equal to plus or minus the square root of n. Okay, so indicating that we isolate our x squared value, then take the square root of both sides, and then we put that plus or minus sign in front of both values. Okay, not both values, just whatever value that number was when we took the square root. So on number 1, again, we have x squared minus 64. I have this x squared term and I have a constant. There's no x term. When that happens, yes, you could do difference of squares factoring. It results in the same answer. I'm just going to throw that out there right now. But if you recognize this, some people don't like factoring. Doing this method is really fast. We're going to isolate x squared. It's just the same process as solving for x. And so many of you are so wonderfully great at solving for x, solving equations, that this should be second nature. So if here's my equal sign, I want to get x squared by itself on the left. So we just add 64 to both sides of the equal sign. So now we have x squared equals positive 64. Again, I want to solve for x, not x squared. So to get an x squared to become an x, I take the square root. What we do to one side, we do to the other. So now on the left, we have regular x, and the square root of 64, that's made up of 8 times 8, so the answer is 8 that comes out. And because we could square 8 to get 64 or square negative 8 to get 64, we say our solution is positive 8 and negative 8. So it's really nice, especially when it comes out that we're working with perfect square values. On number 2, it's just a little bit extra steps here. I have 7x squared plus 8 plus 15. Again, notice there is no x term. We've got an x squared and we've got constants. That's fine. As long as there's not just a regular x, we can use this method. To isolate x squared, first we would subtract 8, just like we would if we were solving for regular x. Now we have 7x squared equals 7. We're still isolating the x squared, so we divide both sides by 7. And we have x squared equals positive 1. We're not done until we take the square root of both sides. Square root, square root. Now we have x is equal to, the square root of 1 is 1, and we throw that plus or minus sign in front. So our solution is this parabola is crossing the x-axis at positive 1 and negative 1. Okay, number 3, we have 81x squared plus 5 equals 21. So again, this whole lesson is about not having any x terms, so I'm not really going to keep repeating that over and over again after this. We want to isolate x squared. So we're going to subtract 5 from both sides. We have 81x squared is equal to 16. Now we have to divide both sides by the number in front of x squared to finish isolating. So divide by 81, divide by 81. At this point, 16 divided by 81 would result in a decimal if we divided. We don't like dealing with decimals, especially when we're dealing with square roots. I'm going to leave this as a fraction. We're going to leave it as 16 over 81. Notice that the numerator and the denominator are both perfect squares. Okay, that's awesome because we can just take the square root of each of those values still. I'm going to take the square root of x squared to make it turn into regular x, and then take the square root of the whole thing, 16 over 81. The square root of 16 is positive 4 here. The square root of 81 is 9, and then we do say plus or minus for the whole thing. So positive or negative 4/9 would be the solution here. Okay, number 4, 8x squared plus 1 equals 17. To solve or isolate this x squared value, first we'll subtract 1 from both sides so that we have 8x squared equals 16. To get x squared by itself, we're going to divide both sides by 8, and we get 2. So x squared is equal to positive 2. We're not done until we take the square root. Remember, you have to turn that x squared into x. We're solving for x, not x squared. So we have x is equal to, now 2 is a prime number. It won't simplify any more than that. So it's just plus or minus the square root of 2. Okay, so it wasn't a perfect square. It was simplified already, so it's going to stay looking like that. Okay, number 5, we have 2x squared minus 9 equals 55. Okay, let's isolate our x squared here. We're going to add 9 to both sides so that we have 2x squared equals 64. And then to get x squared by itself, we divide both sides by 2. So now we're at x squared equals 32. Now, 32, this is not a perfect square. Okay, it would give me a decimal if I was using a TI when I took the square root. So we're going to have to simplify the radical. We're still, again, to get x squared to become x, we take the square root. X is equal to what? Again, I do not want a decimal answer here. We have to break it down. When I take half of 32 to get my starting point, I get 16. 16 is a perfect square. Okay, this is the same thing as 16 times 2. The square root of 16 is what comes out because it's the perfect square. So what's coming out is positive 4. So we're saying x is equal to 4 square root 2. And what do? Just the same one as every other problem, we throw a plus or minus sign out in front of that value. So x equals plus or minus 4 square root 2. Okay, number 6. We have 9x squared plus 3 equals 111. So to isolate x squared, we're going to subtract 3 from both sides. We have 9x squared is equal to 108. And then we divide both sides by 9. Again, all about isolating x squared. So now we have x squared is equal to positive 12. Again, 12 is not a perfect square. There's a part of 12 that is. Let's discover what that is. We're going to take the square root of both sides, because we're following our steps. The square root of x squared is x. Okay, the square root of 12. So again, think of your perfect squares. 1, 4, 9, 16. We don't really need more than that. I'm going to start by taking half of 12. Okay, 12 divided by 2 is 6. So we're here. The next lower number than that, 4. 4 times 3 makes 12. So I know that 4 is the highest perfect square that makes up a factor of 12 that I can take the square root of. So we'll rewrite this as 4 times 3. And then again, what comes out will be the square root of the perfect square. What's coming out is 2. So our answer here, we have x equals 2. The remainder that wasn't the perfect square stays in. And then we throw a plus or minus sign in front because it could be the positive or negative value of this, because squared, they both would result back to 12. All right, number 7, we have 4 minus 3x squared equals negative 77. Isolate the x squared. So we'll solve for x squared here. Here's my equal sign. First, we're going to minus 4 from both sides. We bring down, we have negative 3x squared is equal to, we have negative 81. We're going to divide both sides by negative 3. And x squared is equal to positive 27. So now next we take the square root of both sides to get x solved for. Now 27 isn't a perfect square. Again, at some point, hopefully some perfect square factors are more recognizable to you. You should all be thinking at this point, hopefully, that 9 times 3 makes 27, and 9 is a perfect square, and 3 is prime. So I've kind of found the right combination of numbers. I would rewrite the square root of 27 as the square root of 9 times 3. What can we take the square root of? We can take the square root of 9. It comes out as 3. The other 3, that remainder, stays inside. So x is equal to positive and negative 3 square root 3. Again, if I squared either one of those values, positive 3 square root 3, I would get positive 27. If I had negative 3 square root 3, put it in parentheses and squared it, I'd also get positive 27. We result back to what we had previous to square rooting. Okay, number 8, we have 5x squared plus 10 equals 310. So first, to isolate x squared, we're going to subtract 10 from both sides. And we have 5x squared equals 300. Next, we divide both sides by 5. So we have x squared equals 60. Taking the square root of both sides, we get x, okay, so we're on the right track here, we're almost done. Square root of 60. Well, 60 is not a perfect square. So half of 60 is 30, and I'm gonna, okay, look, let's make a little list here real quick. I should have thought ahead. Half of 60 is 30, so we would start by checking 25. 60 divided by 25 gives a decimal, so it doesn't work. 60 divided by 16 gives a decimal, so it's not the right perfect square factor. 60 divided by 9 gives a decimal, so we're pretty close to being done here. 60 divided by 4, okay, is 15. So we would say 4 times 15, that's 60. 4 and 15 are the two factors we would like to use. So we're going to rewrite this square root of 60 as the square root of 4 times 15. The part we can take the square root of, again, that's the part that comes from the list, the perfect square. The square root of 4 is 2. 15 has to stay underneath because it's not a perfect square. Again, its factors are 3 and 5, both of which are prime. So there's no way to break that down any further. We're going to put a plus or minus sign in front of it. So x is equal to positive and negative 2 square root 15. Okay, our last example here is negative 1/2 x squared plus 1 equals negative 39. Okay, to start off, we're going to subtract 1 from both sides. We have negative 1/2 x squared equals negative 40. And then we are going to multiply both sides by negative 2. Always multiply by the reciprocal to isolate or get rid of fractions. So x squared is equal to positive 80. Okay, remember to turn a squared into not squared, we take the square root of both sides. So what is x equal to? It's equal to the square root of 80. Again, it's not a perfect square, so I'm going to make a quick list right here. I'm going to start by taking half of 80, which is 40. Okay, write that down. So half is what our starting point on the list gives us. That puts us in between these two values. And then you just start by checking. What is 80 divided by 36? We get a decimal, so it's not going to work. 80 divided by 25 is a decimal. 80 divided by 16 is 5. So that works because we didn't get a decimal here. We got another factor. We rewrite the square root of 80 as 16 times 5. Again, we don't change the value, we're just rewriting it in a different way. That's allowed in algebra. The square root of 16 is 4, so 4 gets to come out, the 5 stays underneath, and we're throwing a plus or minus sign in front of it. So x equals positive and negative 4 square root 5. So again, this method only works when there is no x term. Okay, there's an x squared, and then there's constants. And then when that happens, we get x squared on one side of the equal sign, constants on the opposite, take the square root of both sides. And again, if you don't like this process of simplifying the radical by using your list of perfect squares, get yourself a Casio. Like I told you at the beginning of the school year. Get yourself a magic calculator, life will be easier.